Hello, everyone, and welcome to Balliol College's online seminar series. So, I'm your host today, and my name is Vijay Balasubramanian. I'm the George Eastman Professor at Balliol, and I'm a theoretical physicist. So, today we have the pleasure of hearing from Romain Ruzziconi. Romain is a theoretical physicist, and he will tell us about problems in the quantum theory of gravity. So, Romain is a Walker Early Career Fellow here at Balliol and also the Titmarsh Research Fellow at the Mathematical Institute, also here in Oxford. So Romain received his PhD from the Université Libre de Bruxelles in the mathematical physics of fundamental interactions, and then came to Balliol after a stint as a postdoctoral researcher at the University of Vienna, at the Technical University of Vienna. He is a recipient of the Marie Curie Fellowship, a very prestigious postdoctoral fellowship in theoretical physics, and will be using it to spend 2 years next after Balliol at Harvard, following which he will go to the École Polytechnique in Paris. So I give you today Romain Ruzziconi.
Thank you. First, I would like to thank you very much, Vijay, for this nice introduction. And thank you very much to all of you for being here today. So in this presentation, I will discuss apples, black holes, and holograms. So basically, what I will try to do is a historical perspective on the idea that we have about gravity. And hopefully, by the end of the talk, I will reach the kind of state of the art of the things that we are investigating right now. So here's the plan of the lecture. So the big question that I would like to ask is, what is gravity? So I assume that most of you are familiar with the fact that gravity is one of the fundamental interactions of nature. So any object or particles is subjected to gravity. So here I'm giving a few examples where gravity is manifesting itself. So for example, if you observe an apple falling from the tree or the ebb and flow of tides, then these are typical everyday life phenomena that are due to gravity. But also if you observe the movement of planets and galaxies, these are also described by gravitational interactions. And as I will explain in this talk, there are also some very kind of extreme phenomena that are described by gravity, namely gravitational waves and black holes. So something that I would like to argue in this talk is that the changes in the way that we understand the theory of gravity all the time lead to some major scientific revolutions. And so my big question will be, what is the nature of gravity? So here's the plan for the talk. In the first section, I will start with Galileo's law of free fall. Then I will discuss Newton's law of universal gravitation. And after that, I will explain the theory of general relativity by Einstein, which is probably one of the most beautiful theories that we have in physics. After that, I will describe black holes and gravitational waves, which are observable consequences of general relativity. And finally, in the last section, I will mention the idea of quantum gravity and the holographic principle, which is really the state of the art of what we are doing in research. So let me start with the beginning, Galileo's law of free fall. So in the 16th century, there was this idea that was commonly accepted, and which is due to Aristotle. And it's a kind of intuitive idea that all the objects, or at least heavier objects, fall faster than lighter ones. Okay, so that was an idea that was accepted for centuries. But then Galileo disproved this idea using some thought experiment and actual tests. So there is this famous experiment that was performed at the Leaning Tower of Pisa in 1589. And he basically dropped two balls of different masses. And what he observed is that they are actually falling at the same speed. So the original idea of Aristotle that tells that heavier objects are falling faster than lighter ones is actually wrong. And Galileo is kind of formulating this law which is called the law of free fall, and which tells you that all the objects fall at the same speed. Okay, so it's a kind of first revolution in the context of gravity. And this law is already some kind of shows that gravity is somehow universal, so it applies in the same way to all objects and particles. Galileo is also recognized as the father of the scientific method, and he quickly understood the role of mathematics in science. And there is this famous quote from Galileo that the book of nature is written in the language of mathematics. So of course, you might object that this law of free fall is correct. For example, if you consider a hammer and a feather and that you drop them, they will obviously not fall at the same speed. This is of course because of the resistance of the air that we have on Earth. But interestingly, there was an experiment that was realized on the moon. So here I have a short video to show that. So we see an astronaut who has on his right hand a hammer, and on his left hand he has this leather, and he's going to this feather, and he's going to drop them. And what we are going to see is that they fall exactly at the same time. So this is something that it is very surprising for our everyday experience on Earth, but that's what's happening on the moon, and it's because there is no atmosphere on the moon, so you can really perform this experience. So now let me go into the second section, which is about Newton's law of universal gravitation. So there is this famous book of Newton, of Principia, which was written in 1687. And basically, first, this book contains the laws of classical mechanics. So there are three laws. The first is called the law of inertia. And it basically tells you that an object at rest stays at rest, and an object in motion stays in motion at constant velocity unless acted upon by an external force. So that's the principle of inertia. Now, the second law is the law of acceleration, and it tells you that the acceleration of an object is proportional to the force that is exerted on it, and inversely proportional to the mass of the object. Okay, so that's what this famous equation F equal ma tells you. There is also this action-reaction principle, which tells you that to every action, there is always opposed and equal reaction. But in this book of Newton, there is also a very interesting idea, which is called the law of universal gravitation. And this describes the force between two objects, the gravitational force between two objects. So basically, this equation tells you that the gravitational force is proportional to the mass of the two objects. So you have the first mass, little m, and the second mass, big M. And it's inversely proportional to the distance, r squared, of between the two objects. Okay. So that's called the law of universal gravitation. And the legend is that Newton had this idea by just observing some apple falling from the tree in his garden. And interestingly, there is a kind of descendant of this apple tree, which is still standing now in front of Trinity College in Cambridge. So now let me try to revisit this principle of free fall that Galileo discovered within this Newtonian framework. So you can consider, let's say, a ball, which can be, for example, an apple falling from the tree, and m is the mass of the apple. And here m will be the mass of planet Earth. So it will be really the attraction exerted on the apple by the planet Earth that I will measure here. So the force is given by the mass times the acceleration. That's what we saw with the second law. And what this equation tells you is that you can also equal this gravitational force to this expression. So now you can define what we call the gravitational field strength, which is a quantity g here that depends only on the characteristic of the planet Earth. So basically its mass. And you can basically approximate this problem by taking r to be the radius of the Earth. And when you plug this quantity g into this equation, you get that ma, so m times the acceleration, is equal to mg, where g is this gravitational field strength. And you see that the mass of the object appears both in the left and the right-hand side, so you can simplify it, and it implies that the acceleration is given by g, which is a constant, and it's given by 9.8 meter per second square. So from this Newtonian framework, you already derive, in some sense, this law of Galileo that all the bodies fall indeed at the same speed. Okay, so they have all the same acceleration, no matter of their original mass. So of course, to derive this observation, here I use the fact that the inertial mass, which appears in the second Newton's law, so in this equation, is equal to the gravitational mass, so the mass that is entering inside of this equation. And as I will explain in a few minutes, this has some very deep consequences. So the Newton's law of gravity has also some interesting fact, is that it's unifying physics. So there were these Kepler's law describing the motions of planets around the sun. So there are essentially three laws that were known before Newton. The first is called the law of ellipses. It just says that essentially each planet is moving on an ellipse around the sun. So that's the shape of the trajectory. And the sun is sitting at one of the focuses of this ellipse. Then there is the area law, which is a beautiful law which tells you that a line joining a planet and the sun sweeps out equal area in equal times. So this is what is described in blue here on this picture. And finally, you have this law of harmonies, which tells you that the square of the period, so the time that the planet takes to make a complete round around the sun, is proportional to the cube of A, which is the semi-major axis of the orbit. So basically what Newton showed is that you can use this very beautiful equation to explain these three laws. So we can really explain the movement of planets around the sun just by one single equation. So this is an example of unification of physical laws. Quite remarkably, the Newton's law also allowed to predict the existence of a new planet. So after the discovery of Uranus in 1781, it was observed by the astronomers that its orbit deviates slightly from what was computed by Newton's law. Okay? So this suggested that there is actually another planet which is affecting the orbit of Uranus. And Le Verrier in France and independently Adams in England calculated the possible position of this mass of this unknown planet using the Newton's law. And then in 1846, it was actually observed that Neptune, so this new planet that was influencing the orbit of Uranus, was exactly at the position predicted by Newton's law. So it's a kind of triumph of this law of gravity. So an interesting remark is that this Newtonian revolution in physics follows exactly the plan of structural evolution in science, which is described by Thomas Kuhn in his book. So basically, you start with a state of normal science where you have a certain paradigm and a certain framework that allows you to make some prediction about nature and so on. And then you have a lot of work that are performed in that framework. But then by performing some experiments, you notice that there are some anomalies in the measurements with respect to the model that you are using. And when you have a lot of anomalies, a lot of experiments that do not confirm your model, you have a crisis. And to resolve this crisis, you need a scientific revolution. So this is basically a change of paradigm. You need some new framework to explain these anomalies. And this is exactly what Newton did here with his universal law of gravity. So now let me go to the third section, which is about Einstein theory of general relativity, which is one of the most beautiful theory in physics. And here we start with the theory of special relativity, which was established in 1905. And this theory basically gives you some new law for mechanics. So maybe just to give you a bit of context, at that time there was this Newtonian mechanics, which was extremely successful. And on the other hand, you also had these Maxwell's equation describing the gravitational, the electromagnetic field and the theory of light, basically, which were also very successful at that time. But the problem is that in Maxwell's equation, there was this constant, the speed of light, that was appearing. And the fact that the speed of light was constant, independent of any observer, was somehow in contradiction with Newton's law. And so Einstein basically took this idea very seriously and postulated these two kind of principle for his theory of special relativity. So these are very simple principles, but they will have some very deep consequences. So the first is the principle of relativity. It tells you basically that the laws of physics are the same in all inertial frames of reference, which means that no matter of the observer, if you are at rest or if you are moving, the laws of physics will be the same. And there is a second principle, which tells you that the speed of light in the vacuum is the same for all observers, regardless of the motion of the light source or the observer itself. So these are very two simple principles, but they will have some deep consequences. For example, we can show that this leads to time dilatation or length contraction, and also, as I will explain in a minute, the relativity of simultaneity, which means that two events that appear simultaneous in one frame for one observer might not be in another frame. So maybe to understand this idea, we can do this so-called Kedanken experiment. So Einstein was an expert of that. He was actually doing these thought experiments. These were very simple thought experiments that were used to kind of deduce some very profound and important principles about physics. So here I'm going to give an example of such a Kedanken experiment. So let me consider a train that is moving from the left of my slide to the right. And I'm going to consider two observers. One who is sitting in the train, so this is the left situation, and one observer sitting on the platform, and this will be the right picture. So in the first picture, my observer is actually sitting exactly in the center of the train, so in the middle of the train, and he's going to emit two beams of light, one going to the top of the train and the other to the bottom. And of course, what you can show is that since he's sitting exactly in the middle of the train, the two beams of light will reach the extremity of the train at the same time. So these two events are simultaneous. But now let me consider another situation. I consider an observer on the platform, and I also observe this event where the person on the train is emitting the two beams of light. But now, since the train is moving, what the observer on the platform will see is that the beam of light will reach the left extremity of the train before reaching the right extremity, because the light is going at the same speed. Here I'm using this second principle of Einstein. So the speed of light is the same for the two observers. And since the train is moving from the left to the right, that's what the observer will actually see. And so it means that the two events that were simultaneous for the first observer are no longer simultaneous for the second observer. So that's a very deep idea. And that, of course, goes a bit against this Newton's law, where you have to add the velocities together. So the speed of light will not be constant, will not be the same, going to the right or to the left for the observer on the platform. But that's where this principle of special relativity is very different from Newton's law of mechanics. So this paper of special relativity was published in 1905, and this is called the Annus Mirabilis, so the miracle year, because in that year, Einstein also published two important papers, which were revolutions by themselves. So there is this photoelectric paper, which basically is the first idea about quantizing the light with what we call photons. So that's one of the foundation paper of quantum theory. And there was also this paper about Brownian movement, which has also some deep influence on physics. So now the big question is how to make gravitation compatible with special relativity. So now we have new laws of mechanics, and we need to make gravity compatible with that. And it took basically 10 years to Einstein to make that idea precise with what we call the theory of general relativity in 1915. So that was a very complicated problem. That's what it took so much time. And again, this idea, this theory is based on two very simple principles. The first one is called the principle of general covariance. And it tells you that the laws of physics take the same form in all coordinate systems, which means for all observers. So now it does not matter if the observer is moving at a constant speed or if he's accelerated, the laws of physics will be the same if they are formulated properly. And the second principle is called the equivalence principle. And it basically tells you that locally, the effects of gravity are indistinguishable from acceleration. So to give you some kind of flavor of this principle, let me do again a Kedanken experiment, which is a very famous one. So I will consider here an observer who is sitting inside of a box without any window, so he cannot see what is happening outside of the box. And I will consider two different situations. So in the first situation, this box will be inside of a rocket under acceleration, so in the space. And the observer will drop an apple in this box and see what happens. So basically what will happen is that the apple will be falling to the floor of the rocket because of the acceleration. So that's what will happen in this first scenario. But now in the second scenario, I will consider this box sitting on planet Earth without moving, so without any acceleration. And this observer will perform exactly the same experiment. And what we will see will be exactly the same thing. So the apple will fall on the floor because of the gravitational field. So there is no difference between acceleration and gravity. And that's a very deep idea. This is called the equivalence principle. So now as a deep consequence of these two principles, you can show that the mass in the space-time, so for example, you can look at this picture, the mass will deform the structure of the space-time. So there will be some curvature. So that's what this figure is showing. You will get some curvature in the structure of space-time itself. And gravity will be seen as some kind of manifestation of the curvature of the space-time. So maybe to make this idea more precise, let me consider Einstein's equation, which is at the center of the general relativity theory. And this equation basically governed the curvature of the space-time. So let me tell you what this equation means. In the left-hand side, basically, you have this R quantity, which measures, if you want, the curvature of the space-time. So how much you are bending the structure of the space-time once you have a heavy object. And so this is called the Riemann tensor. This is encoded in the Riemann tensor. There is this interesting term that is appearing in this equation. So there is this constant here, which is called the cosmological constant. That's a term that was originally introduced by mistake by Einstein in his equations, or at least for wrong reasons. But as we will see, it plays actually a very important role in modern research. And in the right-hand side of this equation, you have what we call a stress energy tensor. So this T mu nu is called the stress energy tensor. And it basically encodes information about the matter distribution in the space-time. Okay, so if I give you a planet here on this picture, this stress tensor will carry the information about that. And here, what is sitting in front of the stress tensor is just some multiplicative constant, which involves G, the Newton constant. So that also appeared in Newton's law of gravitation. And you also have this speed of light here sitting in the denominator. So basically what this equation tells you is what is the curvature of the space-time once I give you some matter distribution. Okay, so you should really see this equation as governing the curvature of the space-time once I give you some matter distributions. So there is another important component for general relativity, which tells you that matter in free fall follows the curvature of the space-time. So that's also what is depicted in this picture. So if you have this big planet creating, like for example, the sun creating some curvature in the space-time, then you can consider a very small object, like a small planet, going around this object, and it will basically follow the curvature of the space-time. So that's the manifestation of gravity, and it will follow what we call a geodesics, which is basically the shortest path between 2 points. So there is this geodesic equation, which is describing the movement of this small planet here. So it involves the second derivative on the position. So here, x alpha is just the position of this little planet, and tau is just the time. So you take two derivatives of this position. And in the right-hand side, this gamma is essentially a potential for the curvature. So it encodes the information about the curvature in the space-time. And this equation tells you, if you solve this equation for x alpha, you will find the trajectory, the motion of this little planet due to the curvature of the space-time. So you can see this equation as the analog of what we derived in the context of Newton's law, where we saw that the acceleration of an object is equal to this gravitational field strength, g. So this is really the analog of that, because the second derivative of the position is really the acceleration, and this gamma is really the potential for the gravitational field, namely the analog of this g. So the physicist Wheeler had a very nice sentence to summarize what is happening in general relativity. So basically, space-time tells matter how to move. So this is the second part that I was explaining here, that it tells you how the matter is moving inside of space-time because of the curvature. And the second part tells you that matter tells space-time how to curve. So this is what is described by Einstein's equations. So an interesting fact about general relativity is that it was used to predict some observable phenomena. So at the time of when general relativity was kind of published, there was a problem which was known by astronomers, which is called the Mercury's perihelion shifts. So basically, Mercury is one of the planets in the solar system, which is orbiting around the sun, around an ellipse. And what was shown is that this ellipse had a precession with time. So it was changing with time. And what we call the perihelion is basically the point in Mercury's orbit, which is the closest to the sun. So this is represented on this picture. This is each time where Mercury is as its closest point to the sun. And of course, because of the precession of the ellipses around the sun, then the perihelion is changing over time. And part of this change was already predicted by Newton's law, so this was understood. But there was still a little anomaly that was not predicted or understood using Newton's law of mechanics. And what Einstein did, using his theory of general relativity, is that indeed you can use Einstein's equations, so what are called the relativistic correction, to show that Mercury's orbit is actually completely predicted by these equations. So you can really compute the precise perihelion shift of Mercury. And his result matched with the observed anomaly perfectly. So that was the first sign that indeed general relativity was the right theory for gravity. So another interesting prediction, which is maybe even more spectacular, is called gravitational lensing. So it's the idea that if you have a big object like our sun, for example, it will curve the structure of the space-time. And therefore, if you have a star which is very far away, emitting some light, the beam of light here emitted by the star will be deviated by the curvature of the sun, okay, of the space-time created by the sun. And if you are on Earth and that you're observing the star from very far away, what you will see is that the observed star will be there in the sun. So you will observe the star at the wrong position in the sky because of this deviation of the light ray. And this deviation was also predicted by Einstein. And in May 1919, during a total solar eclipse, Arthur Eddington measured the position of stars near the sun edge, and he showed that indeed there was this predicted deviation happening for the position of the stars in the sky. So that was a kind of a triumph for general relativity. Okay, so now the fourth section is about black holes and gravitational waves, which are some kind of very dramatic events which are predicted by general relativity. Let me start with the idea of black holes, and more precisely with the idea of dark stars that was already proposed by John Mitchell in 1784. And it's an idea that was proposed in the context of Newtonian mechanics, so general relativity was not yet known. And it's based on the concept of what we call escape velocity. So the escape velocity is just the minimum speed of that an object needs to escape the gravitational pull of a massive body, like a planet, a star, or as I will explain in a minute, a black hole, without any further propulsion. Okay, so there is a kind of explicit formula for this escape velocity that depends on the mass of the planet or the star, and also the distance or the radius of this object. So to give you some intuition, if you fire some cannonball here on Earth, the faster the cannonball is, the further away the ball will reach the floor. And if you fire with very high speed, then you can send this ball in orbit. So that's called the orbital velocity. And if you use a bit even more energy, then you can send this ball away from the gravitation of Earth. So this is called the escape velocity. Okay, so that's really this idea that you escape from the gravitational field exerted by planet Earth. So on Earth, this escape velocity is given by 11.2 kilometers per second from the surface. So that's the velocity that you need to reach to escape the gravitational field on Earth. On the Sun, it's much bigger. It's given by 617.5 kilometers per second. So that's much bigger because the Sun is, of course, more massive. So its gravitational field is much bigger. So now the idea of a dark star is basically an object so massive and compact that not even light can escape. Okay, so it means that the escape velocity will be bigger than the speed of light, and the speed of light is given by 300,000 kilometers per second. So that's really huge compared to the scale that we are used to in our solar system. So now let me come to the idea of black hole in the context of general relativity. So when Einstein published his equation, he was not expecting to find some kind of exact solutions to these equations. But very surprisingly, a few months after publishing these equations, Carl Schwarzschild found an explicit solution. Okay, this is called the Schwarzschild solution. And this solution was very mysterious because there is a radius. If you study this solution of Einstein's equation, beyond which nothing can escape, and this is called the black hole horizon. So there is a kind of sphere from which nothing can escape, not even light. And there was also this observation that curvature diverges at a point, which is called the black hole singularity, and which is sitting inside of this black hole horizon. Okay. Then in the 30s, Chandrasekhar, Oppenheimer, and Snyder describe how a massive star can actually collapse into a point and indeed create a black hole with this infinite curvature. An important step in the development of black holes was done by Kerr, who discovered an exact solution for a rotating black hole. So again, a solution of general relativity. So in 1963. So these are the kind of black holes that you observe in the sky. They are rotating black holes. And then in 1965, there was this beautiful and very rigorous proof of Roger Penrose here in Oxford that indeed, if a sufficiently massive star collapses under gravity, then general relativity predicts that a singularity, namely a point of infinite density, must form inside a black hole. Okay, so that's a prediction of Penrose using some very rigorous mathematics, and this is called the singularity theorem. So then some X-ray telescope found this Sinus X1, which is a binary system. And basically the astronomers observed that there was a blue giant star orbiting around an invisible companion. And this was the first evidence, observable evidence of the existence of a black hole, so in 1971. But maybe the most striking evidence for the existence of black hole was done in 2019 with this first direct image of a black hole. So this was taken by the Event Horizon Telescope for a black hole situated about 55 million light years away. So that's very far away. So this is really a technical achievement to be able to take a picture from so far away. And basically what you can see on this picture, so you have some kind of halo of light here, um, uh, and this light is emitted from matter and energy falling inside of the black hole. But because of the acceleration, there is a lot of high energy photons that are emitted, and that's what we can observe from Earth. And in the center of this image, you have this black region, which is really the black hole beyond which nothing can escape, including light. So this picture, right after this picture, there was a Nobel Prize awarded for black holes. First to Roger Penrose for the proof of existence of a black hole from a theoretical perspective. And then to Reinhard Genzel and Andrea Ghez for their investigation, their observation of supermassive black hole in the center of the Milky Way. So that was some kind of absolute evidence for the existence of black holes. So now another kind of dramatic event predicted by general relativity are the gravitational waves. So the concept of waves in physics are just some kind of propagation of energy in a medium. That's how you can define a wave. And an example of that in the everyday life is this are the ripples at the surface of water. So that's what is represented on this picture. Or the sound in the air is also another example of such a wave. But the gravitational waves do not really require a medium to propagate. They are really ripples in the fabric of space-time. So I told you earlier that a massive object were curving the structure of the space-time. And this curvature or these ripples in the space-time can actually propagate with waves. So this is what these gravitational waves are. And something remarkable is that they propagate at the speed of light, so very fast in the space-time. And they carry some energy away from the sources emitting these gravitational waves. So there are distortion in the space-time itself. That's what is very interesting about them. So these gravitational waves were predicted by Einstein in linear theory, so by looking at the weak field approximations. But there was a long debate about their existence at a nonlinear level, so in the full Einstein theory of general relativity. And Einstein himself also had some very strong doubts about their existence. But then there was this kind of very down to earth argument by Feynman, which is called the sticky bed argument, which was formulated in a conference in 1957. And he basically said that a passing gravitational waves moves beads along a road, generating heat from friction, so it must be carrying some energy. And this kind of argument was supported by the works of Bondi and Pirani, who showed very rigorously that indeed gravitational waves exist and they are carrying some energy from the sources. So the first gravitational wave event was observed in 2015 by the LIGO and Virgo collaboration. So LIGO here stands for Laser Interferometer Gravitational Wave Observatory. So it's basically a huge interferometer. So you can see a picture of it here. And the way that it works, so you have some mirrors and you send some beams of light between these mirrors, and this will create some interferences. So there will be some destructive or interferences. And what will happen is that if there is a gravitational wave, then the distance between these mirrors will change. So you will produce some interferences, and that you will be able to observe to probe the gravitational waves passing through the mirrors. And for this first event, the gravitational wave that was observed was produced by two merging black holes. So it was, in some sense, an experimental confirmation of the gravitational waves 100 years after their prediction by Einstein. And there is a kind of very nice simulation of that you can see of these black hole mergers. So I have a very short video of that that I can show you. So you can see here a binary system of two black holes, okay, rotating around each other. And you see that the curvature of the space-time around is manifest because of these very heavy objects. And what will happen is that this black hole will accelerate and at some point will merge together and create some very strong gravitational waves that we will observe. So that's happening at this moment where the two black holes are actually merging together. You can see that there is an emission of gravitational waves which is propagating in the space-time, and that's what we have been able to observe. So now let me go into the last section, which is about quantum gravity and the holographic principle. So as I told you before, gravity governs the world at a very large scale. So by that, I mean, if you observe an apple falling from the tree, the movement of the planets around the sun, or the movements of galaxies, these are very big scales for physics. But there is another important theory in physics, which is called the quantum theory. And this theory governs the world at very small scales, namely at the scale of elementary particles. So for example, if you know the standard model of particle physics, this will be a quantum theory describing that. And this has been actually very successful. So these two theories, namely general relativity describing gravity and the quantum theory describing the physics at the level of elementary particles, are two completely different frameworks. So one theory is classical, general relativity, and the other theory is quantum. And for example, a classical theory is characterized by the fact that it's deterministic, which means that if I give you, for example, the distribution of matter in the space-time, you are able to predict exactly what is the curvature of the space-time. If you are able to compute and solve Einstein's equation, you will be able to predict exactly what will be the curvature of the space-time, and then what is the movements of the particles propagating in this space-time. So this is in contrast with quantum mechanics, which can essentially only give you some probabilities of things to happen. So it's a probabilistic theory in that sense. Also, an important fact about general relativity is that it's continuous. So the structure of the space-time is a smooth manifold. And this contrasts with quantum theory, where the quantities are discretized. So basically, I mentioned before this photoelectric effect where Einstein kind of postulated or put the idea that the light was made out of photons, so these quanta of light. And this is where this name quantum theory is coming from. Okay, so you have some kind of quanta of energy. So black holes are extremely compact and heavy objects, which means that you have some extremely strong gravitational interactions happening inside of a black hole. And this is happening at very small scale because of the gravitational field. Everything is kind of contracted in some very small regions. So you need some quantum theory. So it means that if you need to describe a black hole, you need both gravity and quantum theory, which is what we call a quantum theory of gravity. So there have been several attempts to find such a theory. For example, string theory is probably the most popular. There is also a theory of loop quantum gravity, which is trying to quantize the structure of space-time itself. There is also twistor theory, which is something which is an expertise here in Oxford that has been used to try to quantize gravity. But maybe let me focus on string theory, which is the most popular approach. So this theory is based on the fact that elementary particles are maybe not exactly point particles, but they are actually very small strings that are oscillating. And depending on their mode of vibration, they will produce some different particles. So for example, they will produce either electrons or protons, so that or quarks more precisely. So all the elementary particles are just very small vibrating strings. Another interesting idea about string theory is that our world, so that's a prediction of string theory, might have some extra dimensions. So string theory is predicting that the universe should be 10-dimensional. But for the moment, we are only observing 4 dimensions, so 3 dimensions of space and 1 dimension of time. So the other dimension will be compactified, and they will be so small that we cannot observe them with the current instruments. One of the nice features about string theory is that it avoids the black hole singularity that I mentioned before, where the curvature of the space-time is really diverging, because there is a minimal length, which is called the string length. So you can not go beyond that. So you avoid, in some sense, this point singularity. So an interesting idea about black holes is that they've been shown to be thermodynamic objects. So they have a temperature, and in particular, they radiate. So these quantum effects have been computed by Stephen Hawking in the 70s. And in some sense, they show that black holes are not completely black. So they are emitting some radiation that in principle, so we cannot do it with our current experiment, but it should be unobservable. And in particular, as a thermodynamic object, black holes have an entropy. So if you don't know what the entropy is, it's basically a quantity that measures the amount of information that you need to characterize an object. Okay, so that's a kind of intuitive idea of how to describe entropy. And a surprising fact about black hole is that the entropy is proportional to the area of the black hole horizon, not the volume. Okay, so that's a surprising theoretical fact about black holes. And there is this very famous Bekenstein-Hawking entropy formula, which is given here. So in the left-hand side, this is the entropy. And it tells you that it is equal to this quantity in the right-hand side. So Kb here is just the Boltzmann constant. C is the speed of light. H bar is the Planck constant. And G is the Newton's constant. And A is the area of the black hole horizon. So this interesting observation that the information that you need to characterize a black hole can be actually encoded on the horizon of a black hole suggested this idea of holographic principle. So in the early 90s, it was suggested by Toft and Leonard Susskind that indeed gravity is holographic. So this idea is just a bit the same idea than the standard hologram that we have, for example, in Star Wars. So you have this idea that you can construct a three-dimensional image, so here of Princess Leia, using some information on a two-dimensional surface. Okay, so from this source here, you can really emit a three-dimensional image. So this is based on the same idea that our universe itself could be a huge hologram, and the information could be somehow encoded at the boundary of the universe. So there is this holographic principle, which is a bit which is the formulation of this idea. So it tells you that gravity in a given space-time region can be encoded on a lower dimensional boundary of that region. So that's really what the holographic principle is. So then this idea of holography was made a bit more precise by Juan Maldacena, who is a physicist in Princeton, with the famous ADS-CFT correspondence. So that was established in 1997. And so what is this ADS-CFT correspondence? So it's a correspondence or a relation, if you want, between gravity in d+1 dimensions in what we call anti-de Sitter spacetime. So these are spacetime that have a negative cosmological constant. So remember that before I introduced in Einstein's equation this term, which is called the cosmological constant term. So it involves this lambda. And this quantity that was introduced by, for some reasons historically, can actually be used to solve Einstein's equation. And anti-de Sitter spacetime is a spacetime for which this lambda is negative. Okay, so that's what it means to be anti-de Sitter. And so this correspondence is between a spacetime which is anti-de Sitter and a conformal field theory, which is living on the d-dimensional boundary, so in one dimension lower than the spacetime itself. So in the right-hand side of this slide, you have a representation of ADS spacetime, which is just this kind of cylinder, and the dual field theory, if you want, the theory that encodes information about gravity is living on the boundary of this cylinder, so in one dimension less. So conformal field theories are basically scale invariant theories that are very well known in physics and that are sometimes used to describe phase transitions in physics, for example. So using this ADS-CFT correspondence, you can actually tackle some very hard problems and deduce some very deep things, deep lessons about quantum gravity using this lower dimensional field theory, so this conformal field theory living in one dimension lower. So it's a very powerful tool to study quantum gravity somehow a bit in an indirect way. So the problem is that our universe is not really anti-de Sitter. So you can show that with the observation, it has been shown that the cosmological constant is positive. It's not negative. So the question is, does holography still make sense for our universe, the observable universe? Isn't it just some kind of weird mathematical model? And let me say that this cosmological constant that has been observed in our universe is extremely small, which means that for most of the observable phenomena, so if you're interested by collider physics or most of the astrophysical phenomena, you can actually neglect the effect of this cosmological constant and take it to be zero. Okay, so that's what happens for most of the physical effects that we are observing every day. And the question is, can you try to formulate holography for a spacetime which has a vanishing cosmological constant? So these spacetimes have been represented here on the right of my slide. So you see that they look completely different compared to these anti-de Sitter spacetimes. So you have to kind of reinvent holography in that context. And this is part of my ongoing research. So I'm focusing on kind of deduce holography for spacetime that look like our universe, which have a vanishing cosmological constant. And this is, in particular, there is a very active group in Oxford, and we have published some papers in collaboration with Professor Fernando Alde and Lionel Mason here in the group in Oxford. So one of the key features of this duality or this flat space holography is that the dual theory is no longer a conformal field theory. So it's no longer this theory to describe quantum gravity in the bulk. You need something else. And this is what we call a Carolian field theory. And here the word Carol refers to Lewis Carroll, who was the author of Alice in Wonderland. And the reason for which we call that a Carolian field theory is that the physics that is involved there is a bit reminiscent of what you can read in Alice in Wonderland, and in particular in this Matty party, where the time intervals are completely arbitrary and the causality is completely different to what we experience in our everyday life. Okay, so that's what I wanted to say. So thank you very much for your attention. So I'm very happy to answer any question you would have on this presentation, of course.
Great, wonderful. Thank you so much, Romain. So we already have a number of questions in the question and answer box. Everyone watching the talk is more than welcome to put in questions in the Q&A box, and we'll get through as many of them as we can in the time. So, Romain, I'll read out the questions to you, and
Yes.
you can take them as you wish. So the first question is from Hans-Johann Glock. This was a question that came in actually quite early during your seminar, and you presented two Gedanken experiments, and you may want to recall the second one that you gave, and the question
Right. Mhm.
was the relationship with the curvature of space-time. What was the exact reason you were talking about the second Gedanken experiment?
Right. So this was this experiment in the context of general relativity. So let me maybe show the slides again. I think this was this slide, right?
I think so.
So I was showing this Gedanken experiment to illustrate this equivalence principle that was formulated by Einstein, which basically tells you that the effects of gravity are indistinguishable from acceleration. So it's a kind of very surprising and deep idea. And this is illustrated in this figure. So if you have an observer who is in a rocket under constant acceleration and is dropping an apple, the apple will fall on the floor because of the acceleration. So that's exactly the same situation than when you are in your car and you are accelerating, you are stuck on your seat because of the acceleration. So that's exactly what is happening in the left-hand side here. And in the right-hand side, this is just the usual experience that we have of gravity and the apple falling because of the gravitational field exerted by Earth. And the claim is that there is no way for an observer, if there is no window to see what is happening outside, to distinguish these two situations. So it's a kind of very deep idea that leads to this idea that the space-time is actually, you have to think about the space-time as an entity that can be curved by the gravitational field.
Wonderful. Thank you for that answer. So there's a second question by an anonymous attendee, which would be great to get your views on. The first question is, you mentioned gravitational waves, but what produces them? Because something must make a source. We have to wave our hands in water to make water wave in the bath. So what
Right.
produces them? And then there's a secondary question, which is what kind of energy do they propagate? Perhaps you could take those in turn.
Yes. So the event that I was mentioning for the gravitational waves here was the merging of the black holes. So that's the short video that I showed where we see these two black holes. It's a binary system of black holes rotating around each other. And basically, when the two black holes are merging together to form a big black hole, at that moment, there is an important emission of gravitational waves. And that's what we have observed through this event. So that's an example of event that can produce some gravitational waves in the space-time. And typically, you can also observe gravitational waves for other events like neutron stars, for example. So there are other binary systems with very massive objects. And you can also observe gravitational waves in that context. And there have been observations about that in using the LIGO-Virgo experiments. So now what is carried by gravitational waves? So this is essentially some form of energy. So you know that energy can have some different form. It can have some different manifestation. So gravitational waves, in some sense, is some manifestation of some propagation of the energy in the space-time. And basically, the intuition is that if an object, if you have like a binary system emitting some gravitational waves, that the mass of the system, which is a form of energy in some sense, is going to decrease with time because of the emission of these gravitational waves. So it's just a kind of way to carry away some energy from the sources. And there is this Feynman quote that you can use it to do a lot of things, like to boil water, for example, if we were smart enough. Um,
Great, thank you. So then there is the next question is from Richard Pardy. It's a very interesting question. And Richard says, we know there are electromagnetic waves like light, and we also have gravitational waves, which you have discussed. What about waves associated with other possible forces of nature? And in particular, Richard wonders whether, we hear about neutrinos coming to the Earth from distant stellar explosions and what have you, could this be considered some kind of wave radiation of some kind?
Right, right. Very good question. So I mentioned in this slide this theory of this quantum theory. And inside of this theory, there is a very deep kind of duality between a particle description and a wave description. So basically, you can show that elementary particles have two types of description. Either you can see them as particles. That's the kind of intuitive picture that neutrinos or electrons are particles. But you can also see them as waves. And you need this picture to really appreciate the quantum theory and in particular its probabilistic feature. So for example, when we are thinking about neutrino, you could see them as either particles that you detect coming from space, or you could also see them as some waves propagating, and basically there will be some kind of probability related to these waves. And that's where this nature of this probabilistic nature of quantum theory is coming from. So you can have some constructive or destructive interferences between these waves. And that's why sometimes you will have some very high probability for some events to happen, like a neutrino detection, or some very low probability. So that will be some other examples of context where you have some waves at a very fundamental level, I think.
Great, wonderful. So there's another question. There are excellent questions in the question box. I think the Balliol alumni seem to be very, very much on the ball with this kind of physics. So Hans-Johann Glock has another question, and his question is, why does the validity of the holographic principle depend on having a negative cosmological constant as opposed to the vanishing cosmological constant we thought we had, or the positive one that we think we might have? So what is going on there?
Yeah, it's an extremely good question. So actually, this ADS-CFT correspondence that I mentioned, which is the holographic principle for anti-de Sitter spacetime, so spacetime with a negative cosmological constant, was discovered in the context of string theory. And it was basically obtained by taking two limits inside of this theory of quantum gravity, which is string theory. And by taking these two limits, you can show that on one side of the limit, you really get anti-de Sitter spacetime. So these spacetime are natural objects or natural background in string theory. And what you can show is that, for example, space-time with a positive cosmological constant, it's not even clear if they are compatible with string theory. So there are a lot of research about that recently to understand if our universe itself can be in somehow a solution of string theory. And it's a bit the same story with space-time, which are flat in some sense. So it's a very complicated problem to obtain holography in that context. So in this original derivation of Maldacena, when taking these two limits in string theory, it's absolutely crucial that the cosmological constant is negative for the argument to work. And you cannot repeat simply this argument with a vanishing cosmological constant, which means that essentially you have to start from zero and propose a new holographic duality. Maybe let me mention that something that we are trying to do in current research is to start from what we know in ADS-CFT correspondence. And a nice thing that you could try to do is to take in everything in your theory, lambda going to zero. So you start with a non-vanishing cosmological constant and you take it to zero. But the big question is, what is happening to the dual theory, this conformal field theory, if you try to do that? And that's basically what we are trying to understand. And this is related to this Carolian theory that I was mentioning. So this is what we call the Carolian limit, which is something very, maybe it's a bit technical to enter in these details, but that's some kind of possible road to obtain holography for space-time with a vanishing cosmological constant. So understanding this limit on the other side of the duality.
Great, thank you. Now, next you have a compliment from Wayne Henderson, who says that was a really great, perfectly pitched presentation, which
Thank
I
you.
agree with. So I thought I would just read it out to you. Um, and there's a cluster of questions about string theory and a cluster of questions about black holes. So I'd like to collect them together. So in order to do that, while I'm thinking about it, I'm going to use my moderator privileges to first upgrade a question about teaching at Balliol, since it's so important to what we do as scholars and academics. There's a question here from Richard Norman, who says, thanks, Romain, for a great lecture. Could you say a little bit about your experience teaching students in this and other areas of your research during your fellowship at Balliol, especially in areas such as this, where the state-of-art research seems to be advancing our understanding of quite fundamental pillars of the subject? As a teacher and scholar myself, I think this is a really important question. How do we convey knowledge to the world?
Right. It's a very good question. So I agree that teaching is a very important part actually of our job. And it's something that I really enjoy, like sharing my experience and what I know about physics with interested and motivated students. And what I should say about Oxford is that we are very lucky because we get extremely good students, and they are very interested and curious and ask a lot of questions. And so I gave some tutorials about quantum theory to second year undergrad in mathematics. And they were super interested about physics, even if originally they were coming more from a pure math background. But I was super lucky for that. They were really asking questions far beyond what was expected from them at that stage, so far beyond the kind of problem sheet that they have to solve for the course. And I haven't had a student asking some questions, I would say, at a master's level, and he was in second year undergrad. So that was really a kind of a pleasure to teach at Balliol for that. And what I also enjoy is that we have very small group of students, which means that we can really interact with them. And each tutorial is really some kind of personal teaching. So we can really kind of address their specific questions, and depending on the students, it can change completely. So for that, I would say it's a very nice experience.
Wonderful. And I'll also take one more Oxford-related question before we're coming back to the physics one. So Harold Hamley writes, you mentioned Alice and the Tea Party. So as Lewis Carroll was an Oxford mathematician, I wonder if any of his work on maths or logic is at all relevant to the issues that you are exploring.
Yeah, that's a funny question. So indeed, so the name Carroll was not because of Lewis Carroll. So let me explain maybe this. So the original paper about what we call the Carolian limit was published in 1965 by a French physicist. So his name is Lévy-Leblanc. And so it was basically, just to give you a bit of context, there is this Galilean limit that was very well known. Starting from special relativity, you can take this speed of light going to infinity that gives you the Galilean limit. And very late, so in 65, this Carolian limit was found. This is the opposite limit. So this corresponds to taking c going to 0 instead of c going to 0 to infinity limit. So that's what we call the Carolian limit. And Lévy-Leblanc, in his paper, because I think he was a very kind of cultivated and he had some humor, because of the kind of strange phenomena that were happening in this Carolian world, he decided to give the name of Carol to this c going to 0 limit that he implemented in his paper. But so this Carolian limit has nothing to do with the original work of Lewis Carroll that he had done in mathematics, but it's coming because of this inspiring Alice in Wonderland novel.
Yeah, great indeed. You know, um, walking around the Oxford, seeing the haunts of Lewis Carroll and Tolkien and others. It's a lot
He's
of
a star here. I think it's the right place to do Carolian physics.
yes, exactly. Right. So there's a cluster of questions about string theory that I'm going to collect together. So there's one question that says, does string theory predict compactifications of dimensions to be continuous or discrete? So that's one. A parallel one, this is from Gareth Jones, by the way. A parallel one is, can one dimension be more compactified than the other? So that's the second one, about the relative scales of compactification of different dimensions. And I'll throw in one there. Suppose you had these compactified dimensions. Why haven't we noticed yet? And because there's supposed to be all these extra dimensions. You would have thought we would have seen them and wave my hands and I don't feel them. And then there is a question from Andy Watson, which is related to those two, which says, you said that string theory is at the minimum length scale. What determines this length? Or is this an arbitrary value that the theory cannot predict? So that's a group of questions. Perhaps you could address them together.
Yes, thank you. Thank you very much for the question. So I think these are already very precise questions, actually. So maybe about first the compactification that is arising in string theory. So that's this idea that I was mentioning there. So the question is about, are the dimension continuous? So the answer is yes. And basically, there is a kind of way to compactify the spacetime. So you cannot use any compactification. So it has to be compatible in some sense with string theory. And so there are some background on which you can compactify. This is called Kaluza-Klein compactification and so on. And actually, one of the problems maybe of string theory is that there are so many ways to compactify that. So maybe let me take a step back. So what you want to do is to produce or to make some predictions about the real world. And you have to start from string theory, which is living in 10 dimensions. So what you have to prescribe in this way, going from 10 dimensions to 4 dimensions, which is the real world, is the way that you compactify the spacetime. And there are many ways to do it, many ways which are compatible with string theory. And that's a kind of big problem right now. It's called string phenomenology, is to kind of make sense of all this compactification that will lead to the real world. So there are many ways to do it. And for example, there are also many scales for this compactification. It's not automatically a sphere. It can be very complicated compactification. So that also, I guess, answer this second question about the scale of the different dimensions that are compactified. So why the extra dimension have not been noticed? So it's an interesting question. One of the reasons is that we are here talking about quantum gravity, which is something really happening at the Planck scale, which is extremely small and very far from any experiments that we can perform right now. So it's at a very small scale. It's just that it's too small to be observed, basically. And it's not known currently at which scale these extra dimensions will appear, depending on your model and how you compactify the space-time. So there are different options and possibilities. There are even some models that are predicting that it will be obtained maybe in the 10 following years. Maybe we'll observe these. We'll have at least some evidences of these extra dimensions. There are some experiments that are done in Vienna in that direction, for example. And I find it very fascinating. And there was a question about this string length. So that's indeed a parameter in the theory. That's something that you have to provide. And one thing which is elegant about string theory is that basically in Einstein's equation or in Newtonian mechanics, you have a lot of constant of nature. You have the speed of light, the Newton constant, and the Boltzmann constants, and so on. So you have a lot of constants of nature. But string theory is kind of providing a unified framework. And there is only one parameter that you have to tune, and then all the rest basically is fixed by your choice of compactification of the extra dimension, for example. So it's a very elegant theory that provides a kind of unification of physics.
Wonderful. Thank you for that detailed answer. An anonymous attendee has a request that perhaps you could share your slides. I don't know if you would like to do that or not, but perhaps I could suggest that you would talk with the administrators to see if that's
Sure, I'm happy to share the material, yes.
so perhaps you will talk to the administrators to figure out how to do that. Great, wonderful. There are then three related questions about black holes. So one is, do you have any thoughts about microscopic black holes? We possibly have, which may have arisen in the very early universe, or maybe detect from which the radiation may be more easily visible or something. Then there's a question that say, how does the holographic principle explain the loss of information in a black hole? And I think you will have various things to say about that, and whether there is a loss or not a loss. And then the third question is related to that. So it says, instead of saying that there's a loss of information, so I should have said the first question is by Christopher Lord, the second question was by Joseph Muscat, and the third question by Jim Crawford says the reverse about the information loss. It says, I think I've read about a theory of conservation of information. As one sometimes says, quantum mechanics conserves information. Anyway, so if so, then when a copy of Through the Looking Glass drops into a black hole, what information from the book would be encoded on the surface of the black hole? So three related questions.
Very good questions, actually. So maybe the first question about microscopic black hole. In principle, they could exist. Nothing tells you that these should not exist. There is something that I mentioned before about black holes radiating. So there is this Hawking radiation that I mentioned here. And it means that in some sense, because of this radiation that is emitted, so this can be computed at a quantum level by looking at some fields around the black hole, and these black holes can evaporate. And so that's actually the idea, is that the black hole itself can evaporate because of this radiation. So it means that a black hole has a lifetime. It's not eternal in principle because of these quantum effects. And for astrophysical black holes, this lifetime is extremely long. So we will probably not observe in a lifetime kind of evaporation of a black hole. But if you look at microscopic black hole, because they are very small, they evaporate very quickly. Okay, so that's something that you can show, is that the time life of a black hole is inversely proportional to its mass in some sense. So in principle, microscopic black holes can exist, but they will evaporate very quickly. But it's a kind of interesting kind of object. So now about the holographic principle and why it explains this, or it does not explain the loss of information. So maybe let me give you a bit of context about that. So the information paradox was essentially formulated by Hawking, is that if you have objects falling inside of a black hole, you are basically losing the information of the object. So they are just falling inside of the black hole, but the black hole is evaporating. And the way it evaporates, it completely forgets about what fell inside of the black hole. So it means that once the black hole is evaporated, you lost all the information about what fell inside of the black hole. So you have a loss of information in that sense. So that's kind of combinations of general relativity and quantum field theory that leads to this conclusion. And the question is it true if we had a theory of quantum gravity, would there still be a quantum information, a black hole information paradox? And the holographic principle seems to suggest that it's not the case. The reason is that the theory, which is dual to gravity, to quantum gravity in anti-de Sitter spacetime, is unitary. So it's a unitary theory, which means that if you want, the probability are conserved in time. So the information is conserved, in other words. So that's a way maybe to see that from the dual perspective, that conservation, that information should be conserved in time. But it's an indirect argument, in the sense that this argument is performed from the point of view of the dual theory, where we know that information is conserved. And because of this correspondence between quantum gravity in the bulk and field theory at the boundary, there should be some kind of equivalence in the statement. So that's the first kind of proof, or an indirect proof, of the conservation of energy. There also have been a lot of works concerning the conservation of information, how to explain the black hole information paradox, with these works of Hylands, for example, and so in the context of quantum gravity. So this has been done in two-dimensional quantum gravity, essentially, for most of these discussions, and people have shown that if you take some other saddle point of quantum gravity. So that's a bit a technical term, but you can basically explain this black hole information paradox from the bulk perspective. So that's a kind of very interesting ideas and recent developments. So I would say that recent developments suggest that conservation, that the information is indeed conserved, and that there is no loss of information, but you need to take into account the full quantum gravity to understand that, or this powerful holographic principle.
Wonderful. We have time for two more questions, and fortunately, there are exactly two more questions in the question box.
Very good.
Let's go take the first one first, which is that this is from Philip Asquith, who writes, you mentioned that gravitational waves travel at the speed of light. Can you comment on the speed of gravitational action? I take this to mean that can you comment on the speed at which one object can act upon another?
Very good. So yeah, very good question. So in the case of Newton's law of gravity, it was thought that everything was instantaneous. So objects were acting on each other very far away, in a completely instantaneous way. But now with the case of general relativity, we understand that the information about the gravitational field is propagating in the space-time. And therefore, it means that the information about some change in the gravitational field takes some time to propagate from one object to the other. And the time that it takes is precisely the time that it will take to the light to propagate from one object to the other. So it means that the information does not propagate instantaneously. It takes some time because of these propagation of gravitational waves.
Excellent. And for the last question, so before we take the last question, I want to do a little advertisement for the next Balliol lecture so that we don't miss that advertisement at the end. So the next lecture will be held on Tuesday, June 10th. It will be by Professor Peter Tufano. And the title of the lecture is Sound and Fury Signifying Nothing, Business Alliances and Climate. Please come. You will enjoy it greatly. Now, let me say there's one more question, and the last question is by Mark Falcon. It's a very important question, and the question says, thank you, Dr. Ruzziconi, for such an interesting lecture. You mentioned some very important questions from the philosophy of science, such as Kuhn's paradigm shift and the wave-particle paradox. Should all physicists and scientists also study philosophy? I think there's a particularly important question for Balliol with such a distinguished history in philosophy.
Yes, so it's a great question. So actually, I should say that personally, my first interest for physics came from some philosophical questions that I had about, the world and the universe, where is the universe coming from, and so on. And I understood that philosophy, the physics could actually answer these questions, at least partially, provide some interesting answers to these questions. So that's what led me to study physics and mathematics. So I think you cannot really be interested in physics without having some taste for philosophy. It's a kind of, these two goes together, and I think this should also be part of the courses of a physicist, to get at some point some courses about philosophy. I could not say that all the physicists are interested by philosophy. Maybe some of them are interested by physics because they like solving puzzles, for example. So it's a completely different motivation. We all like solving puzzles, but I would say so. Different people have different motivations, but definitely I think philosophy should be some kind of driving force for this field, because we want to answer some fundamental questions about the world and the universe, and this is starting with philosophy.
As a fellow theoretical physicist, I couldn't agree more. So on that beautiful note, let me thank you very much for this very enlightening lecture. And
thank you very much to all of you for attending, and thank you, Vijay, for sharing the lecture.
Wonderful. So we will say good night now.
Thank you very much. Goodbye.